Becky does chemistry.
Hey guys, it's Becky. Welcome back to my channel. Today I'm going to show you how to do an acid catalyzed hydrolysis of an amide. So first I'm going to start out drawing my reactants. I'm introducing hydronium in this step because we're in an acidic solution courtesy of our hydrochloric acid. So this lone pair of electrons on my carbonyl oxygen located in the HOMO non-bonding sp2 orbital will attack the sigma star LUMO of my hydrogen-oxygen bond on the hydronium, breaking the bond to form water and protonating my carbonyl oxygen. So now that we have a positive charge on my oxygen, my carbonyl carbon is extra susceptible to nucleophilic attack by water. So this lone pair in the HOMO non-bonding sp3 orbital of water attacks the LUMO pi star on the carbonyl, breaking the double bond between carbon and oxygen, moving those electrons back up on the oxygen and restoring its neutral charge. So now I'm going to draw out my tetrahedral intermediate with a positive charge on the oxygen that came from the water. So in order to reduce that oxygen back to its neutral charge, it is deprotonated by another water molecule which uses its lone pair in the HOMO non-bonding sp3 orbital to attack the LUMO sigma star between the hydrogen and the oxygen, breaking that bond and creating another molecule of hydronium and neutralizing that charge in the oxygen that is now part of our tetrahedral. So now in this next step, we are going to protonate the nitrogen of our amide, which is going to make it a better leaving group. So we're going to do that using this very acidic hydronium that we have. The lone pair located in the HOMO non-bonding sp3 orbital of our nitrogen will attack the sigma star LUMO between our hydrogen and oxygen of our hydronium, reverting it back to water again. But now I'm going to start with drawing out our tetrahedral again, but now we're going to kick out the leaving group. So this lone pair on our carbonyl oxygen in the HOMO non-bonding sp3 orbital is going to attack the sigma star LUMO between the carbonyl carbon and the nitrogen, breaking that bond and kicking out nitrogen in the process of reforming a pi bond between carbon and oxygen. So I'm going to draw out what this looks like now. We have broken the ring officially. So now that this bond between carbon and nitrogen is broken, the last step we have to achieve the desired products is the deprotonation of our carbonyl oxygen in order to obtain a carboxylic acid. So the lone pair in the HOMO non-bonding sp3 orbital of water will attack that sigma star LUMO between the carbonyl oxygen and that hydrogen, breaking the bond and reforming our initial catalyst hydronium. So now I'm going to just finish drawing out what our products are going to be in our hydronium, and there you have it. So here's what an energy diagram for this reaction might look like. The valleys represent the 5 intermediates as seen earlier, and the peaks are all my transition states, which I have drawn out here. Note that the partial charges for each transition state are always positive, as my charge during a transition will be somewhere between +1 and neutral. The formation of my tetrahedral has the highest energy peak, which makes it the rate determining step. Then at step 5, when we break the ring, we see the largest downhill decrease. This is because we finally relieve the ring strain shown here. You could say that this step drives the reaction forward. Now overall, we see that this reaction has a negative delta G, making it a spontaneous reaction. This also means that our K will be greater than 1 because our reaction favors the products. Now if we wanted to speed up the forward reaction, Le Chatelier's principle tells us we can add more products. However, unlike an acid-promoted hydrolysis of an amide that requires equal moles of amide and acid, this amide requires less acid because we regenerate hydronium in the last step. Therefore, we only need to add more amide.
Science rules.